Okay. Good morning, everybody. I hope everyone's having a wonderful day. So today I'm going to be talking about splay trees. Now, you might ask, Dan, what is a splay tree? Well, today I'm going to be giving you kind of an introduction to splay trees. I'm not going to be able to, in the time I have, go into the deep, interesting theory around splay trees, because honestly, if I tried to do it within this next lecture, it would be absolutely a travesty to the topic, because this is a very interesting topic in its own right. And I encourage you, if you find yourself interested in these splay trees, to seek out more information about them. There's so many interesting theoretic properties that these data structures have, but they're very, very simple to implement. That's what that's one of the strange things about this, is that very often in data structures, what we have is we try to maintain some property throughout the execution of operations for that data structure. So just as an example, just to make sure I'm clear, we're going to be talking about self-adjusting binary search trees. You've seen an example of such a thing. In 210, you probably have seen AVL trees. AVL trees are self-balancing trees. They guarantee that the height before any one of the operations like insertion, removals, and searches, all of them will have it so that the height is big theta of log n, so it has a logarithmic height. And that means that when you put the binary search tree operations in place, since they are all taking in proportion of the height of the tree, they'll take logarithmic time, which is wonderful. But to do this, they often impose a very strict structure. So for example, with an AVL tree, you end up having this so-called height balance property where you store internally in each node a height or a balance factor, and you just see that, make sure that this doesn't get too out of whack. And if it gets out of whack, you have to perform a rotation or single or double rotations, so some combination of these, to correct the balancing of the tree. And it does this at every node, so it works its way from that node where the first imbalance occurs, and it works its way up to the root, performing any modifications it needs to do. For certain operations, it only happens once. Other times, it may happen multiple times. Another example of such a thing is called a red-black tree. I won't be talking about red-black trees, but they're another example of a self-balancing tree. They have the same theoretic properties as the AVL tree from an asymptotic standpoint. So they guarantee still the logarithmic insertions, searches, and deletions. But it does it through a different process, a very rigid structure. It's actually kind of related to, if you've ever seen 2-4 trees, there actually is a relationship between 2-4 trees and red-black trees. But I'm not going to talk so much about those. But I want to emphasize one thing. And this is something that I've done up to this point in probably every data structure you've probably seen up to this point. They always rely on this property that I hold some so-called invariance. So every single time I do some operation, like an insertion or removal, wherever I modify the tree or modify my data structure, what I do is I simply take it and say, hey, look, it doesn't satisfy the following properties. So for example, with an AVL tree, you maintain such a thing called a height balance property. With the heap that we talked about, remember we talked about binary heaps? The binary heaps maintain two properties, the heap order property and the binary search tree property. And we wanted to make sure that it got maintained at every stage when we make a modification to the data structure, right? And when we did that, we guaranteed that the height of the heap was always logarithmic, right? So that's a paradigm that we've been using, and that's very standard, and I've told you that this is very standard to do. This is going to be one of those strange examples where that is not true. And I really wanted to highlight this one for you because it is, at least the data structures community, people like to lovingly call this like the one example of like black magic in data structures. It's not really magic, it's just amortization. So what a splay tree will do is it's going to attempt to balance a tree, but instead of trying to rigidly keep track of certain properties amongst all the nodes, instead, I'm going to try to take two ideas that I know work pretty good and slam them together to guarantee that the height is going to get kind of fixed. So the way I like to think about this is, imagine there's some guy in the corner, some guy or girl somewhere over there, and every time I make a modification to the structure, I pull up my poking stick and I say, hey, look. Can you make it a little bit more balanced for me? And I poke them. I poke them like this. And then they'll say, oh, okay, I'll do it. I'll rotate it for you or something. That's going to be sort of the approach that the Splay Tree takes, as opposed to this rigid one where every single time I look to make sure that this very special property is being maintained at every stage. So that's what I mean by lazily attempt. So just imagine me sitting in the corner there with a bag of chips, and I'm just like, and then I'm like, hey, look, fix the tree. Hey, I poke you. So what you're going to see, and this is what's going to be kind of mind-blowing about this, is that all I'm going to do is I'm going to take everything you know about binary search trees, and I'm just going to add one operation that you're going to do after each one of those. So if you do an insertion, you're going to do this operation I'm going to tell you in a moment. If you do a removal, you're going to do this operation I'm going to tell you. If you do a search, I'm going to tell you to do this operation. And it's built around the intuition of the following two things. So there's two ideas I'm going to kind of slam together here. I'm going to take an idea from the AVL trees, this idea of a rotation. So I'm going to use rebalancing operations. Now in theory, I can't go into the details about this with the time I have. But the big thing I want to point out to you is that double rotations typically perform better at balancing the tree than just single rotations. Now, if you recall back to AVL trees, there are some special properties that the rotations have in the algorithms that you use for the rebalancing. I'm not going to go into those details here, but the double rotations have a very special property about how they balance the tree. We would like to use these as much as possible, these rotations, in particular double rotations. So I just want to remind you what a rotation is. So you don't need to remember everything about AVL trees. I'm just going to show you what a rotation is. So here's a picture. So this is the picture I want you to remember. So imagine I have two nodes, X and Y, and imagine it has two subtrees for X. I'll call this, say, T1, this T2, and this T3. And there may be more nodes up here. There may be more nodes up there. One thing, whenever you're implementing a structure like these, just like the AVL trees, you always have to remember that there could be a parent for Y. So you always have to hang on to the references for these things so you don't lose them. References or pointers, however you want to say it. So in a rotation, what I do is I try to, if I apply rotation to X, what I do is I promote X and I demote Y. So what I do is I promote X to become the parent of Y. And now I swap one of the subtrees, so X's right subtree, and pass it over to Y. Like so. So this is what I would call a rotation or a single rotation. So I can go back and forth between these two. So sometimes people call this a right rotate. So if I go from the left picture to the right picture, they often call this a right rotation. I'll call it a right rotate. And if you go from the right to the left, we call that a left rotate or left rotation. So when I go this way, what I do is I apply an operation called rotate, and I apply it to X. So I promote X, and I demote Y. And then when I do the left rotate, I promote Y, and I demote X. So I use rotate on Y. And that's how the two relate to one another. Whoops. Let me make sure. Remember, there could be that parent that's still kicking around. Whoops, I lost my marker. So does everybody remember by any odd chance these rotations? So this is just a rotation. Just give me a thumbs up if you recall this at all, or if you've seen this before. If not, that's okay. I'm going to be going through some examples. Okay, good. So we're going to take this idea. So what we're going to do is we're going to try to employ as many double rotations as possible, which are comprised of two rotate operations. So the idea is that by using these rotations, I can maintain the binary search tree property, which is the one that maintains all the keys in my nodes. So just in this example here, notice that I have T1, then X, then T2, then Y, and then I have T3. So notice that this has that ordering, and when I do the rotation, it's still T1, X, T2, Y, than T3 if I read it in order. So if I do an in-order traversal on this subtree, notice that the order doesn't change. That's a very important reason why we use these rotations for the splay tree. The other reason is that, like I said, double rotations are better than single rotations. So we're going to use those in our procedure for this operation I'm going to describe in a moment. The other one is this idea that I'm going to try shortening paths. So I can take the longer queries that happen in the tree and I want to shorten those. Why? So let me give you a motivation behind this. And mainly because I'm not going to be able to go through the careful analysis with you, because the analysis for the splay tree, I want to give you some intuition behind this and why we're doing this. So I want to ask you a fundamental question. Why is it that a binary search tree performs slowly? So if I do a search, why does it perform slowly? So just think of any binary search tree. Why does it perform slowly? Does anybody have any ideas? So if I tell you why does a binary search tree perform slowly, everything is on one side. That's a good answer. So that's an example of when the binary search tree gets in its worst possible form, the so-called degenerate tree, where it just looks like a big chain that goes one side down the tree, this way or that way, and it ends up running in linear time, right? That's the worst case with a binary search tree. That's the very worst thing you can have happen with a binary search tree. So if I look at any one, so it checks the value, make sure that they're lowest to highest. Well, it's in a very similar vein. It's a very similar vein. Now, I want you to think about what was mentioned about this idea of the chain. But also, I want you to think about if, say, for example, I wanted to balance the tree. In an AVL tree, what I do is I try to maintain at every given node some constant fraction of the nodes being on one side or the other side for any one of the nodes. And that's usually how self-balancing trees work, is they always have it where every one of the nodes maintains some constant factor difference between their heights. And if I do this at every node, then the difference is every time I go down, it always goes down by the same amount. So just to give you an idea, so let's take those two ideas and kind of slam them together. So if I know that I want to balance the tree, what I would like it to be is I would like to have those paths be really, really short, right? But look at it from the perspective of something like an AVL tree where we try to maintain heights at a given node. So if I look at a given node and I know, hey, look, the search query is going to take a while from this node to wherever it is, you'd agree with me that it's going to have a lot of descendants, right? And those descendants are going to be further down in the tree. So the intuition behind the splay tree is I'm going to try to take these nodes, which in the terms of amortized complexity, if I were to use something like the potential method, which is one way you can analyze this, there's another way you can use the banker's method. These search queries, when I go all the way down to the really expensive ones, because they're further down, but it's also because at one given node, there's lots of descendants. So what I would like to do is take those nodes that have lots of descendants, which in contrast, the nodes down here have lots of ancestors. Whenever I encounter one of these that has a lot of descendants, I'm going to move it up in the tree to its root so that it has less, it maintains less potential to make it so that these ones down here, all those ones with lots and lots of ancestors, have less ancestors. So that I could try to balance it off by moving up those expensive nodes to the higher parts of the tree. And in contrast, because I use these rebalancing operations, I'm going to probably, I may drag some of those nodes that are going to take longer up a little bit. So this is just an informal way of me to describe why these two ideas together might be interesting to slam together. And this is effectively the idea of what we're going to call the splay operation. So from a practical standpoint, another thing you can also think about is that, say, for example, you want to have a tree where you have it where you access the certain nodes very frequently. This splay tree actually is a very natural way of describing structures that do this. So notice every time I access or change the tree, what I'm going to do is I'm going to try to shorten the path. So I'm going to drag that node whenever I access it up to the root, and I'm going to use rebalancing operations to get it up to the root. So if I can do this, then every time I access it again, it's going to be further up in the tree. So it can be closer to the root. Closer to the root, of course, means that there are less operations I have to do. And as a consequence, if I think about it from any one of those really long children, well, the children with many, many ancestors, if I reduce the number of descendants a given node has, and it has many, so that's very lopsided if you think about it like that. If I axe off one of them, then there's going to be less descendants for that more expensive node to deal with. So I'm just going to give potential, take that potential, and I'm going to give it by promoting that node up to the root using rotations. So I just want to give you just an idea of why these two ideas work together nicely. So these rotations are going to make sure that the tree stays in this binary search tree property is going to be maintained. The other thing is that I would like to take these nodes that cause this heavy imbalance. I want to throw them as close as I can to the root. And I'm going to do this as lazily as possible by just doing it after every single binary search tree operation I do. So I'm going to describe, so I just want to make a couple remarks before we proceed to talking about this splay operation. So just, so I want to point out that the splay tree, it maintains efficient amortized complexities. So I'll talk more about what I mean by this later. Complexities for operations. So all of our insertions, removals, and searches, it's going to maintain a really nice efficiency just like a balanced search tree would. But it's not going to actually do that. Instead, it's going to do this lazy operation, this lazy splay operation every single time I make any adjustment or I look at something in the tree. So it maintains efficient amortized complexities. And if you're wondering, its analysis is from the potential method. So if you use the potential method, which I remember I haven't given you an example, that's why I'm not going to go into those details here. But if you find yourself curious, I think the textbook actually, the Weiss book, goes into more detail about this particular approach, I think. But there's also analysis using the bankers method. The whole idea is that by taking these very expensive nodes, the ones that take a while to get to in the tree, by moving them to the root, I basically obfuscate the cost that it takes me to search for it. By moving it to the root, it's kind of like they cancel each other out, sort of. So when I do the search, that's an expensive operation, but every time I move it to the root, I've sort of paid it off a little bit. That's sort of the intuition behind why I do this. So there's this potential method, or the bankers method is used to get the results I'm going to tell you later. So just hopefully this gives you an idea of what we're going to be in for. And believe it or not, this is a really simple data structure to implement. If you know how to implement a binary search tree and you know how to implement a rotation, then you know how to implement a splay tree. That's how simple it is. It's actually even easier to implement than an AVL tree, which is kind of interesting in its own right. So, like I said, I'm going to give you more of an introduction to this topic. So I want to kind of just walk you through just how the splay tree works. And I'm going to give you its results based on just this intuition I gave you. So I'm just going to keep this rotation here because I'm going to need it. I'm just going to talk about the splay operation. Then we're going to do a couple of examples. Then I'll show you how you use the splay operation. Then we'll end off with some results. So like I said, if I had all the time in the world, I would do at least a week on this topic. It's a very fascinating data structure. There's so many things I can tell you about it. So I'm going to talk about the splay operation. So the splay operation works as follows. So a splay operation on a node X. So if I pick some node X, it moves X to the root of the tree T, through a sequence of restructurings. Restructurings of t. And we're going to use rotations to accomplish this. So there are 3 cases. And I'm going to give you the 3 cases over on that board. I've drew you some fun pictures. If you find yourself looking at this and like, okay, well, what does that mean? I have all these pictures in the notes, so don't worry. There are three main cases. Note that the cases I'm going to give you are symmetric as I lose my marker. That was pretty epic. Let me grab that. My apologies. Especially if that made a noise. My apologies. There are 3 main cases. Note that they are symmetric. So I'm just for the sake of time, because you may have seen rotations before, I'm not going to draw all 6 of them. I'm just going to draw you 3 pictures. And they're going to be very similar to what you've seen before with AVL trees. There's 3 main cases. And I'm going to tell you what those are in a moment. We finish when x is the root of t. So what we're going to do is we're going to imagine I give you some node x. So I'm going to tell you what x is for each one of the operations after we do an example or 2, after I talk about what the splay means. And we're going to do these restructurings that are going to have very fun names. And I promise I didn't make them up myself. They sound like things I would make up, but they aren't. They are the technical names for these things. You're going to do these restructurings that will cause x to move up the tree through the rotations. And this rotation will guarantee such a thing because every time it always advances further up the tree. And when we reach the root, that's when we're done. So I'm just going to describe now the mechanism for which we do this. And it's all based on these rotations. So this is just a single rotation here. I'm going to just simply apply rotate in a very particular sequence. Let me just move on over here. So let's move over here. And I drew you some fun pictures. So let's move on over here. Okay, so I got some fun pictures here, and hopefully we can still see the rotate right here, because this might help visualize this a little bit better. Okay, I think we might be able to get it all in here. Okay, excellent, excellent. Everything's here. Perfect. So I'll give you a moment there. Okay, so we're going to have 3 main cases, and they're all going to be based on the rotate operation. So the first case is called the zig-zig. Like I said, I didn't name them these things. That's what they're called. So the zig-zig, now I must stress that some of these rotations are a little different than the ones you see in the AVL tree. One is exactly the same though. So the zig-zig, this is what's going to happen when you have 3, so imagine I tell you I have node x. So I have node x. What I'm going to do is I'm going to consider its parent and then its grandparent if its grandparent exists. So there's going to be 3 nodes that are going to get involved in this process at most. So this is the one that I want to get towards the root, this x right here. So there may exist a parent and then there's a grandparent. So I'm going to work my way up the tree by considering whether x and y are on the left or on the right. This is very similar to how things worked in the AVL tree. So in the zig-zag, it's that x and y are both left children or they are both right children. So the way the zig-zag works is I'm going to do a double rotation. And now the way I do the double rotation is as follows. Now, so what I'm going to do is I'm going to apply rotate on y, and then I'm going to apply rotate on x, So this is what the double rotation is going to look like. Is I'm going to take Y, I'm going to promote Y. That means I'm going to demote Z. Just like I'm just going to do this. Or I always like to think of it like a hanger, where I imagine I have a string that runs across it. So when I do this, I pull the string down, and I'm going to promote the one side that is more heavy up, and I'm going to get the less heavy part going down. That's the intuition, at least with an AVL tree. In the Splay tree, it's more about the potential that could be sitting at a given node. But I'm not going to go into those details here. It's more about, I just want to make sure you understand the mechanism of the zigzag. So all I'm doing is I just perform a double rotation where I apply rotate on Y, so that promotes Y over Z. And then remember, I have to hand over that subtree over to Z. So its left subtree of Z is now T2. And then I apply a rotation on X, which promotes X over Y. Which then now you'll notice that now it just turns in, it looks kind of like I took a mirror image of the whole thing. Does everybody see that? So this is the zigzag operation. Like I said, I didn't make it up. So now there's this second operation called the zigzag. So now this is what you would refer to in the terms of an AVL tree as an LR rotation or an RL rotation. So this is exactly the same as in the AVL tree. So one of X or Y and Y is a left child, then the other is the right child. So we call it a zigzag because it goes zigzag. Zigzag is zigzag. So that's why we call them those things. So zigzag. Notice that X's parent is Y here, and then its parent is Z. Notice that left, right. It could be the other way around where it's right, left. But yeah, you may recall this one from the AVL tree, just it's given a different name. This is the double rotation where all you do is you apply rotate to X twice. And that's all you have to do in the zigzag case. You just apply that double rotation. You do rotate X twice. That's it. Yes, what's up? Okay, so hopefully when I do the examples, you'll see more about how this works. Because I will be doing a couple examples of splaying so that you can see how this works on a tree where I have those dummy or terminal nodes, as you said. But yeah, they're just there just so I don't have to worry about null references. That's really all they are. If you know about them as null references where you not have a child, all you just imagine is there's this dummy node there. That's all it is. Correct. Yes. Okay, so X, Y, and Z. So remember, these are nodes. So these are nodes with keys in them. So when we actually do this, so you'll know because of the binary search tree property, Z's key is going to be bigger than Y's key. But Y's key is, in fact, going to be less than X's key. So the way that this will all be structured is based on how this is. So remember, it could be right-left like this, or it could be left-right like I have in this picture here. So the whole idea is that I'm Okay, so remember the setup here. So I'm imagining I just select a node X. So I just have X. And I'm just going to perform this splay operation on X. So I don't know anything about what happened with X. It's just some node in the tree. So I'm just describing to you just some arbitrary node in the tree. And I'm just considering 3 possibilities that could happen so that I can move X to the root. So what's going to happen is, imagine I give you X, and I'm just going to look at which structure makes sense for the tree. So it may look like this, it may look like this, or it may look like the third case I'm going to have here. So all I do is I identify this with like an if statement. So I just check, oh, is y's child to the left an x? Is z's child to the left a y? Like, this is what you're generally doing when you test for these. But yeah, no, this is just, this picture, these triangles are just subtrees. So there will be a node that roots it. So that's all these are. So just notice that I just haven't drawn the rest parts of these. So these triangles, they might actually end up just being a dummy node. Yes. So in this tree, so it's a binary search tree. So all the nodes, and so in the implementation I'm going to be using in my visualizations, all the internal nodes store data. The leaf nodes don't though. Yeah, so anytime I tell you about X, it's always going to be an internal node. So this should match your intuition when you considered it where you had a node, like you had some node X, then you had like a null reference for the left one and then a null reference for the right one. Yeah, so all I've done, so when I think about this, all I'm doing is, oh yeah, well, this is the power of the rotation. So this is just an aspect that that the rotate operation has, is it always maintains the binary search tree property on the given tree where I root it. Say for example, if I consider the subtree where rooted at Z, if I do this these series of rotations, it always maintains the binary search tree property. If you find yourself not convinced by this picture, for example, just walk yourself back to this and walk through how you do rotate Y on that picture. And then you do the rotate again on X, and you'll see that you end up with the picture I have on the right. Yeah, just remember, all I'm doing is I'm restructuring the tree. So when I promote, so for example, X indeed is less than Y, but remember, the binary search tree says that, okay, if I consider the left subtree of X, all the keys are less than here, and all the ones on this side are greater than, right? So just like over here, if I look at Y, all the keys to its left are less than, all the keys to its right are greater than. So all I've done is I've demoted Y, but notice I still maintain that property right here. Yeah, remember it's a binary search tree. It's not just any old tree. Correct. It's the left. That's why I'm saying that there's actually a symmetric picture to this one where you flip it like this. Yeah, that's exactly it. So just remember, this is a binary search tree, so it has to maintain that property where the keys. So if I look at any one node, all the nodes in its left subtree have to have keys less than it. All the keys in its right subtree have to be bigger than it. Or if you want to have equality, bigger than or equal. Correct. No worries. No, thank you for bringing this up. I know that for some students that they may appreciate that. But yeah, so hopefully that helped clarifies this a little bit. So anyways, what we're going to do is, so I have the zigzag. So remember, that's just a double rotation. This is exactly like it was for the AVL tree, if you remember your AVL tree. This is an LR rotation or RL rotation. So it works exactly the same as that one. Now the third case is the zig case. Now there might be a possibility based on how the tree is structured that Z, this grandparent of X, this grandparent here, doesn't actually exist. That means that Y is the root of the tree. So you might need to have to do a single rotation to get X up to that root. So when we think about that, really, I drew you a picture over here. That's really what this is. So the third case is the zig. So if Z doesn't exist, you just perform a single rotation on X. So you do rotate X. So if you look at my picture I have right here, this is actually just exactly what happens. So I just remember y is the root, so there's nothing up here. So all I do is I perform rotate on x, and then I promote x to be now the root, if that's the case. But yeah, these are really the three cases. So all you do is you repeatedly apply these three cases until x is the root. And that's the splay operation. And you might ask, Dan, what's the complexity of this? Remember, all of those pointer adjustments, remember, rotate, all it is just a bunch of pointer adjustments. I just change the references or pointers of the nodes, and I do a constant number of those operations. So all it does is it actually depends on the tree. I'll talk more about that in a moment. But I want to do some examples. Actually, I may have time to do one example. I'll have a second example in the notes. So let me do one example of splaying at a given node. So let's move on over here. But yeah, I have another example that's going to be in the notes. I have time to do one with you. And then I'm going to talk about how you use this splay operation. And then I'll just summarize some interesting complexity results. Okay, so let me draw an example here out for you. So I'm going to consider the following binary search tree. So imagine I have a 10 as the root, 7, 12. Then I'm going to have 3 as the left child of 7. I'm going to have 9 as the right child of 7. I'm just going to incorporate these little anchor or dummy nodes here. But if you don't like those, you could just simply imagine these were null and you wouldn't even draw these. So that would how it would look in the other way you could represent the binary search tree. So I like to just put these in because I like to make sure you can see another perspective on how you can represent these. It's just an implementation detail. Fundamentally, the algorithms aren't that much different. The only difference now is you can check directly if you're at the bottom of the tree or not, if it's a leaf or not. So it makes the algorithm a little easier to implement. So here's my binary search tree. And I want to do a splay operation. So I'm going to do a splay on the node that has key 13 in it. So these are all the keys for the nodes. So I'm going to have records in these. And what I'm going to do is I'm going to try to get 13 to be the root. So this is what x is in what I was just describing to you. Now I'm going to look at its parent and its grandparent. It indeed has both of these. So this is x, y, and z. So the question is, what do we do to get 13 to move up this tree? So does anybody know what case I should be applying here? Can somebody tell me? So notice I labeled x, y, and z for you to make this a little easier to see. Am I zigzagging or am I zigzagging? Do I zigzag? Yes, I'm zigzagging. So I'm going to zigzag. So what I need to do is I need to do my double rotations where I rotate x twice. So 10 is going to still be up here. This left subtree doesn't really get affected at all by this process. 7, 9. That's a 10. Let me make sure that's clear. That's a 10. Okay. So now, when I'm done this process, so remember, I promote x and I demote y. So remember, think of the hanger. It just goes like this. The 14 gets pulled down this way, and it grabs onto this node this leaf node that has nothing in it. That's what it hangs on to. And then I do a rotate on 13 again, and I promote it over 12. That brings the 12 down. And then it grabs onto the other child of 13 that used to be there, which indeed was another one of these dummy nodes. So I end up with the following. So I end up with 13, 12, 14, 16. Remember, the 16 gets dragged down with the 14 when I promoted 13 that first rotation. So I have 12, 14, and then 16's down here. Am I done yet? I'm not done yet, right? Yes, you can do each rotation you're asking about doing each rotation individually. Now, well, at this stage I could do it because it's just a single rotation I have left. But yeah, no, it's the same concept from the AVL tree. That's all I'm doing. Is I just do each one of these once. So I promote, then I demote. Then I promote, then I demote. So, now, remember, this is still X, right? That's X. It doesn't have a grandparent, though. So it's Y right there. So what do I do? What do I do? What case do I apply? Do I zigzag? Do I zig? Do I zigzag? Do I zig? I zig. I zig. So all I do is I promote 13, I demote 10. So I just apply this right here. So 13, 10, 14, 16. Remember, the subtree that's over here with this 12 gets dragged over to 10 over here. It sort of grabs onto it. 14, 16. The 12 gets traded over here. That's how this rotation works. 7, 3, this is a 7, 3, 9. So that's the resulting tree I have here. So notice that now X is indeed the root, so we're done. So the reason why we call this a splay tree is notice that I've taken the tree and I kind of moved it, I spread it out like this. I splayed it out so that everything that is less than this keys value is to the left and everything to the keys value to the right is bigger. But I move any one of the nodes to this root and that's just X. So that's why we call it a splay tree. It's a splay operation. So it just it moves it up by doing these rotations, and when you're done, you kind of spread it apart, and then you have now two trees where everything on the left of it is smaller, everything that's on the right of it is bigger when it comes to the key values. So I have another example in the notes when I splay the same tree again, where you splayed it on 3. I want to talk how you do these splay operations, and then I got to talk about the time complexity, and then we're going to stop for today. Okay, that's basically all I have to say about splay trees. So let me get to talking about how we actually use the splay operation, because everything about the splay tree, I must stress, is just a binary search tree. I'm just going to add this operation in. So if you know how to work a binary search tree, all you do is you just add this splay operation at the end. That's what makes it so appealing as a data structure. So let me describe to you how we pick X. Because remember, I told you there's this node X. So let me talk about the operations of a splay tree. So I have to tell you what X is. So let's talk about what X is. So I just want to clarify that we're going to augment. That means change or modify. Augment each binary search tree operation with a splay operation. Splay operation on a particular node X. And I'm going to tell you what X is for each one of the operations. That happens after. That happens afterwards. So after you do your search, you're going to apply the splay operation. After you do an insertion, you're going to do the splay operation. After you do a removal, you're going to do the splay operation, the one we just did over here. So if I give you a get operation, this is just search. I'm just searching. So if I give you some key and I want to get the result of, so if I want to know if a given record with key K is in the tree, that's what get does. So you just perform a search. As with a binary search tree. There's two possibilities. If K is found, X is the internal node, the internal node that stores K. So you're just going to pick X to be the node that you have the key K in. That's the one you're going to splay. If the search fails, however, in the algorithm for search, the way it works is that you work your way down the tree, right? In one implementation, when you have it where there aren't these dummy nodes, you work your way all down to the bottom until you hit null, right? In this version where you have these dummy nodes, it's just that it's a leaf node. So there's not much of a difference. It's just that it's more of just a whether you want to deal with null or not. It's like training wheels. I like it. If the search fails, X is the parent of the leaf node, the search reaches. So all you do, so in the search, if you remind you of my picture over on the left side, or when we did our example, I had those little dummy nodes. Those are our leaf nodes. When I failed to get a search, I hit one of these leaves. So I'm just saying, pick the node that is its parent. That's all I'm saying, which will be an internal node that has a record in it. That's what you're going to pick as X. If you weren't doing it with these dummy nodes, you just pick the node that you got to before you hit null. So that's how you do it with the search. That's it. So if you're doing an insertion, so I give you this, I'm calling it put. I give you the key and a value. I insert, so you just perform, insert as with a binary search tree. And if K is not found, because in a dictionary we have unique keys. This is more of a technicality, but I just have to mention that. If K is not found, a new internal node, along with two leaves, I'll just say, call it X. So new internal node X is created. You're just going to splay X. So this newly created node will store the data for our insert. So you just splay this one. The remove K. There's a little bit more detail I have in the notes if you don't remember how to do a removal in a binary search tree. You just splay, you're just going to splay the node X. That is the parent of the removed key, the removed node with key K. So you just simply, because remember, you're going to delete a node in the tree. So you're just going to select the parent of the deleted node. That's what you do in a remove. So that's all you have to do. You just at a splay operation like this. So it's okay if I get 2 minutes from you. I want to summarize the very fascinating thing about the splay tree. Because I have just a couple of things I just want to write down for you. And these are probably the neatest part about the splay tree. This is why I was giving all this intuition. That I also want to leave you off with a pretty epic Thanksgiving. So let me just quickly write this down. So this is what's killer about, not killer as in like a killer app of this data structure. Not only is it simple, notice one thing I will make a remark about is that, remember, I just do the splay operation, I just do it whatever, like I just pick X. Notice I don't have to store anything special about the nodes like in an AVL tree. In an AVL tree, I have to maintain the heights or a balance factor. No such thing exists in this splay tree. It's just a binary search tree and I just do the splay operation. That's it. It's kind of wild. So it's very simple. It's very simple. So here's the complexity things I wanted to talk about. So these are the kind of like the big things I really want to touch upon. So the complexity of splay trees. Now, of course, in worst case time, so the worst case time of a splay tree, it depends on the height of the tree. Well, height h can be big O of n, right? Because it can be a fully degenerate tree, right? So all operations take worst case big O of n time. So that's not what's very interesting about the splay tree. Okay, so now this is what's the killer app of this thing. Let me just write this. This is kind of wild. This is why some people like to refer to the data structure as sort of like black magic. Watch this. So consider a sequence of M operations on a splay tree. So these can be put, get, and remove operations. Which obviously you put the splay operation in after each one. Starting with a splay tree T with no records. Let Ni be the number of records in T after operation I. After operation I, that's an I, operation I, and N be the number of put operations. So N's going to be the number of put operations. So now this is the crazy part. I'm going to get this. I promise I'm going to be done here. Let me see. So the total running time of this, the total running time is going to be big O of M plus the sum from I is equal to 1 to M of log base 2 of Ni. So this is the total running time of this, if I do M operations. Now you can simplify this down, which is big O of M log base 2 of N. And from an amortized standpoint, if I know I have M operations, everybody tell me, what's the amortized complexity of doing all these operations then, if it's M log N for the total running time? Somebody tell me. So the amortized complexity. So the worst case per operation. So What is it? It's not this. In fact, it's actually big O of log n. So by doing this very lazy process, just slightly modifying a binary search tree with this splay operation, you can get big O of log n, or logarithmic time, operations for every operation on your binary search tree, which is wild, right? I just did this very simple thing. I just modified with the splay operation. Isn't that wild? So notice I didn't maintain anything other than, hey, look, I just do the splay operation. And boom, I get amortized complexities of log n. So in practice, it very much can match a lot of these self-balancing trees, and it's much simpler. It's black magic, I swear. It's not really, no, it's just amortized complexity. So that being said, I apologize for going over here a little bit. I apologize for that. When we come back next time, we're going to be starting a brand new topic. We'll be talking about graphs. So that being said, I want to say thank you very much and have yourself a wonderful weekend. I'll see you later.